Okay, so let's take a look here at how interest is determined here, what our money does. Let's suppose I'm looking at my formula and they ask me to explain it. Well, let's say I'm going to invest, I got $100 and I'm going to have an 6% APR and I'm going to compound monthly. Well, at the end of the first compounding period, I'm going to have my original $100 plus what interest do I earn in that first compounding period? I don't earn $6 because I have to take that rate of 6% and I've got to divide it by the number of compounding periods there are in the year. That's what APR means. So at the end of the first month, I'll have $100 plus the interest I earn off that $100, which will be 100 times 0.06 over 12. If I look at this expression, I can factor a 100 out, leaving a 1 plus 0.06 over 12. So if I do that in general over here, I've got a certain principal, and at the end of the first month, I'll have interest earned, which will be the principal times my APR divided by my number of compounding periods. Factor P out of both terms, P times 1 plus R over K. So if we then go ahead and use this same principle again, just in the general case, that's what I've got at the end of the first month. So the end of the second month, I'll have the principal, what I had at the start of the second month, plus what I had at the start of the second month times the interest I earned in that month. I then can look at this long, nasty expression. I can factor out a P times 1 plus R over K. When I do that, it leaves a 1 here, and it leaves R over K there. I then have 1 plus R over K squared. So at the end of the second month, then the second compounding period, I'll have P times 1 plus R over K to the second power. So what they're asking you to do in 17A is just basically explain that when you're earning interest, you're going to certainly have to divide up the annual percentage rate by the number of times you're going to compound per year. You want to know how much money you're going to have total, not just the interest you've earned. That's where the 1 plus is going to come from. And then your outside exponent here is going to be how many times you compound over a 1-year period, where they say you're compounding K times per year. So that's where my K then is going to wind up coming from. So for 17B here, they ask me to consider what happens to this expression P 1 plus R over K to the K as K gets large. Well, by K getting large, let's let K be large and let's use this limit notation that we've developed. It's the limit as K goes to infinity of this. And I want to look at that and I say, well, that should look kind of familiar to me. I've got a denominator going large, and I've got an exponent going large and a 1 plus. That's my definition of E. E is the limit as K goes to infinity, 1 plus 1 over K to the K. So can I make this look like this? And the answer is yes, I can. I need to get that numerator here in the second term to be a 1. I can do that by reciprocating R over K to be 1 over K over R. I know in my definition of E, the denominator and the exponent have to match. So let's get this to be a K over R, so I match. Well, to get it to be a K over R, I know originally I have a K, so to cancel out that R to keep things the same, I'm going to multiply by R. Now I look at this expression, K over R, K over R. This whole expression right here is equivalent to E, because as K approaches infinity, this denominator is going to infinity, this numerator is going to infinity, and they're going to infinity at the same rate, and that's my definition of E, that denominator and exponent have to go to infinity at the same rate. They do here, so I can replace all of this with E, and that still leaves the R that I needed outside to make sure that I was matching up these two things. So that's what they actually wanted to have you show in 17B. So first for 21, they tell you that if you create a line tangent to e to the x at the y-intercept 0, 1, they tell you that it can be shown that the slope of that line equals 1, and therefore the y-intercept of 1, its equation is y equals x plus 1. And they've said then that no, if you're very close, if your x value is very close to 0, the outputs for the line and the curve are going to be about the same. And that allows them to say that, hey, for x close to 0, e to the x is about equal to x plus 1. They ask you to show And again, I'm going to write things just a little bit differently. They ask you to show that 1 plus x to the 1 over x equals e. And the idea is, can you transform this equation into this equation by doing something legitimate? And the answer is, of course I can. If I take the 1 over xth root, right, the 1 over xth root of each side, well, this side's going to match up. I've got the 1 over xth root of x plus 1, and if I take the 1 over xth root up here, I'd simplify, and that's going to get me down to e. In writing, e to the x to the 1 over x goes to e to the x over x, e to the first, which is e, and clearly all I've done on the other side here is I've just taken the 1 over xth root, and I'm done.